Okay, so let us continue. So the next speaker is Professor Arnold Cruzeiro, who will tell us about the variational aspects of Euler and Navier-Stokes.
Okay, so I first would like to thank very much the organizers of this conference for the invitation, for showing the tolerance to have in this conference someone who is not in precisely in the community. And I also would like to thank you in advance for for resisting a talk which is again not exactly in the spirit of this conference. So I'm mainly a stochastic analyst. Sorry. Used to be not that you met it. So I will try to make this talk as light as possible in the sense that I'm going to tell you a story, and I'm not going to be very technical, so you will have time to go for lunch sooner than maybe than the schedule. So okay, so this is about essentially the Euler and Navier-Stokes equation, because this is the main motivation. Well, main motivation behind what I'm going to talk about is variational principles, but it doesn't apply only to these equations. It applies to many others. And before I forget, no, okay, just to do that. And now it works. And I have to do this at each time? Just because I don't know what it is. Okay. And before I forget, this is a joint work with Chen and Tudor Ratiu, who are in the Shanghai University. Okay. So my first, the starting point of my story is the Euler equation. So typically in partial differential, and well, most people that work in actually with Euler and Navier-Stokes, but Navier-Stokes will be a little bit later. With Euler equation, look at the. There should be a pointer here. Yeah, a traditional one. Okay, look at this equation, right? This is a PDE, very well known. The unknowns of the U, which is the velocity of flow. Fluid divergence zero means that the fluid is incompressible. Then it has normally they consider it on some space and with as a Cauchy problem. So with a starting initial condition. So this is the PDE approach of most people that work with Euler equation in particular or other equations. So the math contribution of Arnold in the 60s, remember exactly the year, was to look at a slightly different problem, which apparently looks the same, but it's not exactly the same. So U is indeed the velocity of some flow, but you look at the flow. Okay, so you look at the ODE. Okay, so there is some intersection with the ODE here. So you look at the at some ODE, and so actually you look at the trajectories of the flow and not so much at the velocity. The velocity comes a posteriori. Okay, so you look at the flow. This is called the Lagrangian approach. It's not Arnold's approach, but it's called the Lagrangian approach. You start from a point. And you look at these flows as diffeomorphisms on the or whatever, I mean, what you have as regularity on the underlying manifold. And you look at the problem where you have a starting point and a starting flow, fixed, and a final flow. This is a two-point problem. It's not any longer a Cauchy problem. It's an initial and final problem for ODE. And a posteriori you get. So So the problem is formulated in an infinite dimensional space, which is the space of diffeomorphism. Because you look at these G's, I will always call them G's. The G's are diffeomorphisms. Since you want, if you want the compressibility condition, these are flows that keep the volume measure invariant. That's invariant flows. And now the contribution of Arnold, which looks like a quite easy one once you have seen it, but it's a very deep one, is that this Euler flow is a geodesic on the space of diffeomorphism with respect to L2 metric. Okay. Now, this space is a diffeomorphism, of course, it's very big. It's not quite a manifold in the usual sense. It has some problems. It has a composition structure that makes it sort of a Lie, right? And you have, and the geodesic is precisely the Euler flow. So this was a very important, I mean, more than a remark, I don't know how to call it, but it's really a deep thing, although it's, you can easily convince yourself that it's true with a small computation. But it's very deep because you put geometry into the problems. And geometry gives you a lot of information, in particular concerning the stability of the motion, because it's related to the curvature of the manifold and many other things. So it's really a big thing that was, again, stated by Arnold, Vladimir Arnold in the 60s, and then there was a very famous paper by Evin and Marsden that defined, I mean, really structured the geometry of these spaces. So as a geodesic, you can see it as the minimization of the kinetic energy. So you see, and if you do the variational computation that gives you the critical points, you really see that this is the solution of your other equation very easily. So what is the metric is you have to integrate in time as usual, and you have to integrate in the manifold with respect to volume measure. So this is the kinetic energy in a space of diffeomorphism. And then the U comes after. The U is the derivative time composed with gta minus 1. So the U, the velocity comes after. The problem is a problem of a geodesic on an infinite dimensional space, which is a bit complicated, but it is what it is. Now, there is another community, which is the community of geometric mechanics, that are very used to state variational principles, like this one, not necessarily with kinetic energy, with other Lagrangians, not necessarily in infinite dimensional space, but starting from mechanics problems, so finite dimensional ones. And they have some variational principle and so on. And if you apply formally without thinking of being very rigorous what they do, you get to an equation like this. And actually, this is exactly the same. So the community of geometric mechanics, mainly with coming from Marsden. Well, the paper, remember, it was already by Evin and Marsden. And then there is all the Marsden school. And they also started to do infinite dimensional spaces, in particular in order to study the Euler equation. Well, it applies more or less to any quantitative systems, not necessarily only to Euler, but the Euler was the first one and the most famous one. And as you may know, there are still problems concerning all kinds of problems with respect to this equation, which is very studied and very interesting, very well. So actually, this is geometric mechanics in infinite dimensions. They call them something else, APD, something, but anyway, it's what it is. And nowadays, if you open the book of geometric mechanics, the last chapter maybe of infinite dimensional cases, and it gives you Euler equation. So it sort of a little bit moved the community that was studying it. So who knows, these things always can always change community. So I think.
Can I just ask?
Yeah, please.
What's this? Can you explain the right hand side of the equation?
Okay. I forgot to mention G, which is the group of diffeomorphisms for us that keep measuring their intervals of conservative. G is also a group with composition. Okay, that's I suppose I did. So, and if you have a group, you have the operation add and add stuff, right? And
style is the adjoint with respect to the.
It's the adjoint with respect to the add operation. So if you have a add UV is this star is just
Okay.
with respect to the metric that you have there.
Okay.
It just is. And if you do this in this case, you get it's exactly the same thing as Euler.
This is because the inner product is not necessarily adding variance, so one size might be different from other.
Yeah, yes. And when you do the computation with vector fields, and then you this is the alphametric, and then you have to do this divergence 0, and then you see that the equation is exactly. Okay, so I mean, if somebody here knows geometric mechanics, it would look at this equation, and this is the equation that they always start from. Or somehow, I mean, at least in some cases. Anyway, so what is my aim here with my collaborators is that okay, now you have this theories all only apply to conservative systems because they are critical points of some action and so on. So there's must be conservative. So what about dissipation? I mean, and what about if you add a Laplace to the Navier-Stokes equation, which introduced dissipation to the Euler equation, which gives you Navier-Stokes by introducing this dissipation. So there were some physics papers where they talked about this, but I cannot read them. So there was not much. I mean, if you talk about the dissipative system, there's no variational principle in principle. In short, this is the answer. Although there are some physical stuff which I don't understand. So now the idea was the following, and I'm going to be more detailed after. So, for example, Euler equation, and you put a Laplacian, which is the dissipation, right? If you are a stochastic analyst, you look at the Laplacian and you see Brownian motion in this one-to-one correspondence. So let's try to introduce some deformation in the Lagrangian particle, so in the position, not in the velocity. I keep Navier-Stokes as it is, don't change it. But in the particles, I put some Brownian motion perturbation. That will generate the Laplacian then in the equation. So the vision, again, I'm a physicist, but the vision is that Navier-Stokes flows would describe particles that go around in a random motion. And the velocity that is described by Navier-Stokes equation is actually mean velocity of all these particles. How much of this is realistic in physical terms? I'm not going to discuss this, but it's realistic in mathematical terms, in the sense that it gives you the answer that you want. Okay, so the idea is that you do the same, somehow you do the same, geometry is the same, everything is the same, but instead of computing it on deterministic trajectories, you compute it on stochastic trajectories. So it's a structure, but you just plug in stochastic trajectories, and you get dissipative systems like Navier-Stokes equation and the MHD. And Lagrangian is a classical one. Everything is classical, but computed there. And it is the parenthesis here. This is very much the spirit of the Feynman classical quantum mechanics, but this is another story. Okay. And then some systems, the blue part is just, if you are interested in stochastics, you can also do perturbation in the stochastic question, but not going to talk. Now the last line is that you can also put advected quantities, which are quantities that are transported by the flow. You can also consider that. And for example, if you consider compressible Navier-Stokes, so not incompressible, so not condition neither the zero, so you have a compressible equation, and the density is one advected equation. So you can also treat this kind of systems. So this is the part where when I talk to stochastic analysts, I have to stay in this part very long. But for you, I can go quickly, I'm sure. So if you just have a Lie group, okay, just consider G. G is always for a Lie group. The little g is the element of big G. And I consider a left or a right invariant metric. Most of the time it's left in the literature, but in the deterministic literature, but actually the application sometimes is right. There's not much difference there. And the left invariant or right invariant connection there, which is torsion free. It doesn't have to be Levi-Jigit, it just has to be torsion free. Maybe it doesn't even have to be, but that's what we assume to be, because otherwise there are a lot of computations more. E is the identity element, the tension space to the identity is identified with the Lie algebra, and then you have the tangent map, which is the derivative of a left action or the right action. You are in the right frame. Okay, so this first part, I guess, Bobby knows very well. This semi-direct products are used so that we can consider these advected quantities. So this is a little bit less standard, but it's not very difficult. Well, I don't know the theory of semi-direct products. I just know, I mean, not much more than the definition, actually. So you have a vector space in its dual, and if you have a representation of G of the Lie group on this vector space, this induces some operation, which is actually the moment method in physical terms, which is defined here. It's written with a diamond symbol, typically, and that's just a composition of the A of the others. Okay, but the semi-direct products, I will put them always in red, because if you're not interested in advected quantities, you just forget the red part and just see the black. And if you are interested in advected quantities, then you have to introduce this structure. Okay, now because of the probabilistic part. So as I said, these trajectories that will describe the position of the fluid will be described. It will be sort of like Brownian motion. Brownian motion is probably something that you have heard a lot, and if not, just Google it and you see the motions around. Essentially, what you need to know is that the trajectories are not special anyway. So this is a very, very regular motion, and it's modeled in a probability space. So if you have a probability space and you have some function on it, it is, okay, I don't know if I need this, but let me just state the definition. MW of t, so b little w is for the probabilistic parameter. So if you have a motion such that the expectation with respect to the past, so this is conditional expectation with respect to the past until time s of the motion in time t is equal to ms. So the information that you get at each time, the information from the past is irrelevant. It starts a fraction. Brownian motion is like a semi-Martin. So Brownian motion is a Martin. That's the point. So you can think here something which is more or less like Brownian motion. Then here is a bounded variation part. So something like you can derivate in time. Here you cannot derivate in time. Okay, so just think about this Brownian motion. And something like this is called a semi-Martin. Now, you want to differentiate, or if you want to integrate in time. And as I said, Brownian motion, for example, is not differentiable in any point. So that's a bit of a problem. But fortunately, it was solved in the 50s by Ito, with the Ito couple, and we know how to differentiate. There was also an engineer that also defined some integral, which was called Stotanovich, but I mean, mathematically speaking, Ito calculus became much more famous. And how do? You integrate as you expect, right? If you want to integrate x with respect to y, x and y being semi-Martingale, being things like and not differentiable anywhere, you do this. Or you can do this if you want to Stotanovich, but never mind, just look at this. You consider the x at the left-hand side of the interval of time, and then you consider the okay, consider this.
The step.
That's the step, yes. Now, the interesting thing is that since this is not at all a regular path, if you change and you consider, for example, the right-hand side or something like that, it gives you different answers. And anyway, we take this is the Ito one, and there is a whole calculus. You can compute, once you learn this, you can compute more or less everything with respect to integration, with respect to Ito calculus and also to that. So now, coming back to our problems, the G's in my Lie group, little g's, will not be differentiable in time, will not give an evolution which is differentiable in time, but will be, so the G is a motion on the Lie group, and it's determined by something which is more or less like a Brownian motion, but let's say with some vector fields as coefficient. Plus, this is about the variation part. This is the part which is not, I mean, if you don't have it here, you are in the deterministic case, right? If you have, this is the part that is about the variation, so for computations and derivations doesn't cause any problem. Okay, this is in Stratonovich form, so you don't have to think about this. So my particles, my motion will be of this form always.
This is diagonal formula.
Yes.
So you started with Navier-Stokes.
No, I want.
No, then you said, okay, let's consider instead these Arnold point of view and take all of them.
And take a variational breeze. Okay? Let's consider the Euler point of view. Euler is the Arnold point of view. So Euler is a geodesic in space. That is something which is a critical point of the kinetic energy, right? So I will also define a critical point of the kinetic energy, but compute it on things like this. So not if I don't have this, it will give me Euler.
Very good.
But I will put some perturbation here at the level of the trajectories.
Okay.
And
now you translate these differential equation into the integral model.
Yes, this is written in the integral terms because that I only gave you the definition of the integral. So so this means this.
Okay. So then you cannot find to write down like Euler Lagrange or like those like random.
I use the normal Lagrange. Okay, this you don't have to think. It's another way to write it, but doesn't. Okay. Now this little bit here, which is very important, by the way. I mean, it will be the mean velocity. And why is it the mean velocity? Okay, first of all, you just define the yes.
The H, they are constant, right?
The H, they are vector fields in tangent space. They are constant.
Of
They are constant.
the vector space of the identity.
Yes, yes. And then I have to translate them to parallel translate it to the place where I am.
So is it obvious that this is a martingale?
It is. This part, yes, and plus this is a semi-martingale. No, it is a stochastic integral. Any stochastic integral is a martingale. So, which is kind of important, but again, I'm not going to go into all details. So this U part is very important because at the end, this U part would be some mean velocity that will give you Navier-Stokes. So this mean part, this U part, I will call it D with the connection symbol there. And I call it generalized derivative. And why is it not completely stupid to call it generalized derivative? First of all, because you see, the martingale part, think of it as a Brownian motion. If you, for example, if you want to see the trajectories and simulate them, they go into the direction of u, like if you have a velocity, right? If you have a u, the trajectories go like this, right? U being the velocity field. This is deterministic case. If you consider the perturbation by a semi-martingale, they will just go like this. I mean, they will go in the same direction, but randomly. So the U thing is important, although the trajectories are a little bit shaky, but they go in this U direction. So this is one of the reasons why it's called generalized derivative, in the sense that intuition gives you that. But also if you make this limit, which is a derivative, right? But you take conditional expectation, it gives you this. After, of course, the parallel translation to tangent space again. So it is a sort of derivative in the mean, if you want, after some condition. And also it will give you a sort of mean velocity. So now here we come to the main point, is that, okay, so now forget about the red part. So if you take a G1, this G1 is something like before. It's the G1 and G2, they are things like that. You can change G1 and G2, don't have to have the same HI, but they can also have the same HI. It depends on what you want to do. But they have the same U, okay? So let's see just with one, not considering the red part. So you have a Lagrangian, for example, kinetic energy, if you want to geodetic somehow. You compute it not on the derivative of time, because you don't have a derivative of time, but on this generalized derivative. Okay? But the L is absolutely deterministic. You just compute it on this stochastic part. So it's simply a classical action computed on a stochastic path. And on what you have available as a time derivative, because you don't really have a time derivative. Then if you can consider another one, and this is for the advected quantities part. So you have here something which may depend on alpha, and alpha is the expectation of the pull back by G2 of some alpha naught on U star. Okay, so if you don't want to think about the red part, you don't have concerned advected quantities. No, sorry. Okay, so you have a variational principle. You have to say what are your allowed trajectories. So what them are precisely semi-martingales of the form that I explained before. You also have to say what when you make variations, what kind of variations you allow. And this is again very simple. It's like in geometric mechanics, you consider exponential type solutions of these equations in directions v, and then of course you say that the G1 and the G2, if you want the red part, I should have put this in red, is critical for the action function if for every such variation you have the derivatives here. Okay, so this is what you expect. And now the main theorem is that so you have this DG again as with a fixed U and some coefficients here. Here I have a technical reason, a technical assumption, but I know I'm not going to explain. This is a technical thing. And then so you have to define some vector fields which satisfy this, which are not, this is not completely easy, but they do exist, at least in some.
Is it a scale assumption or is it just an opinion?
It is a little bit of an assumption, but I could relax it. Only would make some extra terms, and I don't want the extra. I don't want these extra terms. Again, it's a bit. I mean, in each Lie group, I have to show to see if I have such objects, but in many examples I do. So they are critical for the action function in the sense defined before, if and only if this U and the alpha, if you want the alpha, satisfy this equation. So now the point is the following. So first, if you don't look at the red part of the semi-direct part, so the advected quantities, let's look just at the other part. So you have the derivative of the LU, which gives you U if you put L as the kinetic energy. You have this at star of U, which you have in the deterministic part. It's exactly the same. Okay. Again, this is the red plus an extra term. Okay. Now, if you have the alpha, you also have this, which you also have in the deterministic case with an equation for the advected quantity. But now, K, with K. K concerns the dissipation, right? And this is why we introduce the stochasticity, the randomness in the particle.
So there is a Laplacian.
Is a Laplacian. Is a second order operator. But actually, the first time we did computations to see what was K, I thought, okay, I'm quit because it is a very strange operator. I did ask some people if they've seen this operator, didn't get the straight answer. So the operator is this one. So it is a bit complicated. So I don't know. Don't know why it is complicated. The point is that if you are in the right invariant case, and if you assume this, together with the Levy-Chib interconnection, I mean, there are various assumptions, right? That first you are in the right invariant case, you have this technical assumption, plus you are using the Levy-Chib interconnection, but this is okay. Then this operator, as is the case star, is this one. And actually this is Laplace delta mu operator, and this one is the Ham operator. So it is a very well known and respectable Laplace. Otherwise, generally speaking, it's a kind of strange second order operator, at least for me. Maybe somebody has seen elsewhere, but this is what the computations give. And thankfully, in some cases, they give good operators. Okay, so right invariant case, again, is just a change of signs and of actions in the left and the right. It's not a big deal. The proof is not extremely complicated because it's a bit like the deterministic case, except that you have to use stochastic calculus. Okay, that's it. And once you know stochastic calculus, it's not very much more complicated. This is just a remark that you can sometimes people in geometric mechanics write these variational principles just like this with some variations of this form, but it is equivalent, so it's a remark. And then, yes, this I already said, if you have no stochastic vector, so if EGT is just u dt, okay, oh well with the left and right. If this is the case, we don't put dt here, but let's say we want to put it here, okay, everything is deterministic. Then you just have exactly this statement, which is a statement that was already known, again, in stochastic, in the geometric mechanics. So we simply add some stochasticity to the result. And when there's no stochasticity, it goes back to the result, which is known. And now everything goes very well in terms of computation and so on, but we are interested in Navier-Stokes and things like, right? Because if you are in finite dimensions, what you get for the U are ordinary differential equations, and you want partial differential equations. So now you have to take everything, but this is again as in Evin and Martin. As the group, the diffeomorphism with a certain regularity, HS, double S border S, some yes. This is an open subspace of the Hilbert manifold HS, the G's, and the tangent space just projector fields on M. It's not quite a Lie algebra because you lose some. I mean, you will start from HS and you lose a little bit. But frankly, for all practical purposes, this is a Lie algebra. I mean, for all kinds of, you compute the same thing, you prove the same things. But you have to repeat all the stuff because it's not like the theory in finite dimension gives you the results in infinite dimension to adjust. But nothing goes wrong. We don't need this to be exactly a Lie group or the other. So you consider the L2 metric on this page. The connection is just a punctual connection, so nothing special. And now you consider the submanifold of this group, of this Lie group, which is the one if you want incompressibility. This is if you want incompressibility. You want that your flows, your elements of G, your path, keep the area measure invariant. And then in this case, you consider this connection, which is when you are in a flat space. Now I will come to a flat torus so that I don't have to be much more complicated. So my manifold, the base is manifold where the trajectories are, we'll think of it as the torus, something flat. So you just have the usual connection on derivation, and then you project it to this situation if you want the divergence free vector field, that is the Lagrangian trajectories that keep the area measure invariant. So this is incompressibility condition in Euler or Navier-Stokes. So how do you get Navier-Stokes equation? You get it by if you are in the torus. Three-dimensional is not critical. You can do any dimension, but three-dimensional is quite a reasonable choice. So you take just HI to be constant vector fields with some constant that is meaningful. Your trajectors are again the U's plus just a Brownian motion because you don't have a special vector fields HI, you just have these. Okay, right. And then if you consider these trajectories and if you do all the machinery, yes.
Now he takes a point of the thought.
epicenter point of the torus. Now this is an example in the torus because it's very easy and you get the equation very easily. Okay, so the action functional again is just the kinetic energy. So you take the derivative in the generalized sense, parallel translate to the point where you are, of course, or well, in this case, to the origin, sorry. And then the theorem in this particular case, it says that this Martin is critical if you only you have Navier-Stokes equation. Okay, so you get simply the usual Navier-Stokes in this case in the world. Now you can get it in a manifold, but I just wanted to be very simple example is this one. Compressible case. The compressible case needs, so you don't have anymore the divergence zero condition, but needs some extra variable. And this variable, remember these alphas that are the pullbacks and some alpha zero. I can put a lot of advected quantities on the motion. I can consider functions, one form, two forms, etc. Going around on the motion. So depending on the alpha zero you choose. If you want just Navier-Stokes compressible, you just consider the density moving around. But you can consider for MHD, which is magneto-electrodynamical equation. Anyway, for more complicated things, there are vector fields going around, or things that are given by vector fields, and then you can also consider them. You do some computation, which is stochastic. So what is the equation of the alpha? Well, you compute. What is if you have form, you compute. Okay, I'm not going to stay. And the simple compressible Navier-Stokes equation, again, in the torus, consists in having a Lagrangian with a density. And then you have to put here, so rho is your advected quantity, is the density. And it will be formulated in this semi-direct approach formulation, sorry. Well, and then you have to put, in order to give the equation, you have to put here the E, which is the fluid's internal energy. P is the pressure. Where is P, by the way? There's no P. There's no P in the action, of course. So I don't know why I wrote it here. Anyway, the DE, yes, it's to define the internal energy is defined like this. It's related to the P. Okay, and then so the action is this, and then you make some computations with DLDU, which is a little bit more. Of course, it gives you the add star, but there is a row here, so you have to compute things. You are not having the divergence zero condition, so you have to do some computation. Okay, it's a bit more complicated, and at the end you get the analogous result, but with this contribution of the advected quantity, is that it's critical for the section functional with internal energy if and only if it satisfies some equation like this. Here I put G1 and G2. Remember one equation for G1 and G2, which were separated things in the contribution of the velocity and contribution of the advected quantity. But if you consider, let's say, all this equal, it gives you this equation here, which is sort of the compressible. Again, I'm in the torus, right? Otherwise, I would have some different Laplacians here, some different operators. But if I'm in the torus, it's flat, so you really see the usual Laplacian coming out, and it gives you this equation. Now, if you look at this equation, this is the Euler part. This is, of course, the Laplacian that comes from my stochastic perturbation. This is what it should be. This thing should not really be here, but depends on the source that you take. There are some physicists that say that it should be here, some others that it should be here, so it's okay. I agree with the second one, so for no reason at all. And then there is an extra term which is lacking if you go, again, if you look at the equation, there should be here the gradient of the divergence of u, and we can get it here, but we have to put something in the actual function, so we can. Except for this term, which is not clear, in the sense that we don't know if it's there or not, but for the dt, we can, the other one, which is gradient of divergence of u, can be put there. I just didn't want to complicate more the action.
I'm a physicist, so.
Oh, good. So you can explain
I know less than you about fluid dynamics. But the next term, some coupling between the dissipation and the variation of volume. If this is correct.
Sorry?
That term that should be there.
This one?
Yeah. It shows some interaction between viscosity, mu as you parameterize it, and then the variation of volume. It only present when there's variation.
Yes, it's variation of volume. Yes, right.
Okay.
Right.
Mm-hmm.
So there is actually a chemist, which is called Bremer, that says that one should not define the velocity as people normally
well, it's a chemist.
define. Yeah, well, it's a chemist. Sorry, but we should put some term like this. So I like him very much, but I don't know what, just because it agrees with this something, but I don't know more about it. Also, okay, so this is actually what the equation is. There is this term that we can treat by changing a little bit the actual functional, and there is no gradient of log of rho. Now, okay, I don't think I'm going to this. You can do this with magneto-electrodynamics equations, which have some, I'll just substitute the equation, but I'm not going to. It's a similar thing.
Can I ask a question about?
Yes, just let me put the equation. Okay, it's an equation like this. So you have D is the density, B is a field that goes around, and then you have more complicated equation, and we can also treat. Okay, just I'm going to say a few words at the end.
Sorry, very important question to understand. Said several times. I consider the torus because it's flat, and it is really just like Laplace.
Yes.
Imagine now you don't have something. Which kind of operator?
I will, if I can take full, I will have the run. So Laplace plus which.
Plus which.
Plus which.
Okay.
Again, this is there is a lot of controversy in this field because controversy in the fluid side. For example, I know a very recent paper by a girl, some woman, I don't remember the name. That wrote a paper about should we use Laplace delta M or should we use Laplace in Navier-Stokes. They are, and this is one argument to use Laplace delta, which actually she quotes. There are
the community in astrophysics, they also worry about this type of problems because of crashing this of black holes.
Yes.
And you have fluid, but you will have also a known flat metric.
Right.
Usually the metrics are not. They don't have large curvature, so the stubs are small. But some people consider them, and then you have to use the run.
The run. Good. So that makes two. I didn't know. Thank you. Okay, so if you are an analyst, and I know there is at least one or two in the room, you will ask the question, the standard question. So, can you improve existence of solutions of these equations with older treasures? Yeah, because this gives you a characterization. geometric one, it gives you information coming from the geometry to the flow. That's okay. But you can also ask yourself, does it give you existence? Because there are many problems. So in the first paper by Evin and Marsden, following the Arnold one, there was a existence local one in solar space. Okay, it was what it was. But here it doesn't work like this because it's not really a geodesic. It's something that's verifies the variational principle. It's not really geodesic, so we cannot import the theorems of geodesics in geometry. Okay, so we just to end the conclusion of my talk, we tried to solve this question in various ways, but we have partial answers in various types of framework. So there is, we have some entropy minimization problems that are very much like, optimal control problems and so on. This gives you some results which are not I mean, they are not the best possible, but there are some partial results. There is some relation with what is called in stochastic differential equations, forward backward stochastic differential equations, because you have, okay, the G is verified an initial condition and the velocity can verify the final condition, so you have an initial and final boundary problem. There are also ways to generalize even more the solution concerning, instead of trajectories, probability measure of trajectories, which was used by Navier for the equation that we tried also to use for Navier-Stokes in particular. We did, in all these approaches, we did something, but I cannot say that we solved the problems Navier-Stokes, but of course that we didn't expect that the problem would become much simpler by using this kind of approach. I mean, the problem is difficult, it stays difficult for the existence low kind of regularity, and that's not how you can win $1 million for the clay prize, because they are always these sort of weak solution. I mean, it's not an approach that gives you a fine regularity to trajectories. Not more than the means from by geometric mechanics. Okay, so I think I will end that here. I hope I didn't bother you too much. So there's some reference. The paper where it written is here. The first one, the second is an initial one where we already had some approach like this. The famous paper Ratiu and Marsden, and the other one by Paul Marsden and Ratiu about having problem, because they are all called Euler point equations of these ones. I will call it here stochastic Euler point. Okay, thank you for your questions.
Thank you. So, any questions or comments?
Maybe can I ask you a super naive question?
Yeah.
So, for example, I was thinking about another problem in geometry, another millennium problem which has been solved. So another $1 million. Ricci flow equation. Is there any?
I don't know. Actually, I don't know. I have a few colleagues that are working with the Ricci flow equation, and they are probabilists, but not the same. So my flat answer is I don't know.
I see. But there are communities in which
yeah,
using stochastic
methods, but well, first I don't know exactly what they're doing, and it's not the same approach, but they are doing this, right?
But for sure they will not win the prize.
No, again, I don't think so. Who knows? I mean, who knows? You should never be too sure. You, sorry.
Yeah. Usually, when you have this noise, average, basically what will happen. It's basically what we also have, which is problem. Even though you don't talk like that, you just talk with the diffusion equation, but you also have fluctuations in physics. So quantities like the deviation of each of the trajectories, they will grow with time. That's
Okay,
one
you can study afterwards, depending on the properties of the velocity that you get, then you can study this kind of deviation, and those are the things. Yes, with respect to this flow, there are a lot of things that can be studied.
No, I understand, but the question was more specific. You would like to have to prove that there is a solution. So I guess, right? I mean, this.
Yeah,
this
it would be nice.
Yeah, that would be nice. But I guess that the thing is that I would expect in physical grounds that the solution, this averages that you take, they become increasingly worse as you flow. Is that you understand? So at some point you just lose that.
Yeah. So most likely local,
I see.
most likely.
Okay.
Any other question? Oh. Okay. If not, let's end this again.